Hi, I'm Dr. Hodges, and welcome back to another episode of Technology and Cybersecurity. Today, we're going to explore one of the most important foundations in all of IT, database and data architecture fundamentals. Every system you interact with, whether it's a mobile app, a website, a business platform, or a cloud-based service, runs on data. And understanding how that data is structured, stored, accessed, and protected is critical, not just for IT and cybersecurity professionals, but for every modern organization. In this episode, I'll walk you through the basic concepts behind databases, the role of data architecture, and why these ideas matter for system performance, analytics, security, and long-term scalability. Let's go ahead and jump in. Now let's talk about what a database actually does at its core. When we think about databases, it's easy to picture big servers or complex systems, but fundamentally, a database exists to store, organize, manage, and retrieve data efficiently. First, databases store data. They act as the digital filing cabinet for everything an application or organization needs. Customer information, transactions, logs, inventory, user profiles, you name it. But simply storing data isn't enough. That brings us to the second function, organizing data. Databases structure information in a way that makes it meaningful and usable. This might mean tables and relationships in a relational database, collections and documents in NoSQL, or objects in modern cloud-native databases. Next, databases manage data, and this includes enforcing rules, maintaining data integrity, handling updates, supporting concurrency, and protecting data against corruption or unauthorized access. Data management is what ensures systems remain accurate, consistent, and reliable even when thousands of people are using them at the same time. Finally, databases are built to retrieve data efficiently. Users expect answers instantly, whether they're running a search query, logging into an app, or analyzing a data set. Databases use indexes, query optimizers, and internal algorithms to return results quickly, even at massive scale. So when you think of a database, think of it not just as storage, but as an intelligent system designed to keep data structured, protected, and immediately accessible. Now let's talk about one of the most important distinctions in modern data architecture, SQL versus NoSQL databases. SQL databases, sometimes called relational databases, store information in structured, table-based formats. Everything has a defined schema, columns, data types, constraints, and this structure ensures consistency and reliability. Because of this, SQL databases excel in situations where data relationships matter and where accuracy is critical, such as financial systems, ERPs, and transactional applications. NoSQL databases, on the other hand, are non-relational. They don't rely on rigid tables or predefined schemas. Instead, they offer flexibility in how data is stored, whether that's key value pairs, documents, graphs, or wide column stores. NoSQL is ideal for rapidly changing data, massive scale, and use cases like social media platforms, IoT data, and real-time analytics. Think of SQL as structured and predictable, and NoSQL as flexible and adaptable. Both play major roles in today's architectures, and choosing between them depends on your application's requirements, scale, and performance needs. When we talk about data architecture, I want you to think beyond just databases. What we're really describing is the entire ecosystem that determines how data lives, moves, and is protected inside an organization. First, we look at how data is stored. This includes the physical and logical structures, databases, data lakes, warehouses, and cloud storage, each designed for different performance, scalability, and analytical needs. Understanding where data lives is the foundation of any effective architecture. Next is how systems integrate. Modern environments rarely operate in isolation. Applications constantly communicate with APIs, message queues, ETL pipelines, and integration services. Good architecture ensures these systems can share information reliably, securely, and efficiently. Then we consider how data flows. This is the life cycle of data, how it's collected, processed, enriched, analyzed, and archived. Mapping data flows helps us eliminate bottlenecks, remove redundancies, and improve both performance and security. Finally, we address how governance is enforced. Governance defines the rules of the road, who owns the data, who can access it, what laws or compliance frameworks apply, and how do we monitor usage for accuracy, privacy, and security. Without governance, data becomes inconsistent, exposed, or unusable at scale. Together, these elements form the backbone of data architecture, shaping how an organization operates, innovates, and secures its most valuable asset, its information. In this section, I want to walk you through the major building blocks of modern data architecture. These are terms you will hear repeatedly in IT and cybersecurity, and understanding how they work together is foundational for designing secure, scalable systems. Let's start with databases. A database is where operational data lives. The data applications read and write in real time. Think of user accounts, transactions, device logs, or configuration data. Databases are structured for fast queries and updates. Next, we have data warehouses. These are optimized for analytics, reporting, and business intelligence. Instead of real-time operations, warehouses focus on historical trends, things like sales reporting, performance dashboards, and forecasting. Warehouses store cleaned, organized data that supports decision-making. Then we have data lakes, which are designed for large volumes of raw, unstructured, or semi-structured data. Data lakes allow organizations to store information before deciding how it will be used. This is where logs, sensor data, images, and large data sets typically land. Lakes are especially popular in machine learning and AI workflows. Feeding these systems are ETL and ELT pipelines. ETL stands for extract, transform, load, traditionally used for cleaning data before putting it into a warehouse. ELT flips the process, loading raw data first and transforming it later, which works well for cloud-scale environments. Pipelines are the backbone of data movement and integration. Another critical component is metadata, essentially data about data. Metadata tells us where data came from, how it was formatted, how it has changed over time, and who has accessed it. Good metadata makes systems more searchable, auditable, and governable. Finally, we have data governance, which ties everything together. Governance ensures that data is accurate, consistent, secure, and compliant. It defines roles, responsibilities, policies, and access controls. In cybersecurity, governance is essential for protecting sensitive data, managing risk, and enforcing standards like CMMC, NIST, and ISO. Together, these components form the core of modern data architecture and directly impact system design, security posture, and organizational decision-making. Now let's take a moment to distinguish two major types of database workloads that organizations rely on every day, OLTP and OLAP. OLTP stands for Online Transaction Processing, and this is what we refer to as operational data. These systems are designed for high-volume, real-time transactions. Think about banking systems, retail checkouts, booking systems, or healthcare check-ins. Every one of those actions, swiping a card, submitting a form, updating inventory, is a transaction processed instantly. OLTP databases are optimized for speed, accuracy, and concurrency. They support thousands of users performing small, quick operations all at once. This is the heartbeat of day-to-day business operations. On the other side, we have OLAP, Online Analytical Processing, which we classify as analytical data. OLAP systems are not about handling fast transactions. Instead, they support deep analysis, reporting, and decision-making. This is where organizations look at trends, compare quarterly performance, analyze customer behavior, or build dashboards for executives. Instead of small transactions, OLAP systems process large, complex queries across massive data sets. They're optimized for reading and aggregating data, not updating it. So in short, OLTP keeps the business running, handling real-time operational activity. OLAP helps the business understand itself, turning historical and aggregated data into insights. Understanding the difference between the two is critical because they serve completely different purposes, even though they both rely on well-structured data systems. On this slide, I'm highlighting three core characteristics that define modern analytical data environments, especially data warehouses and analytical systems. First, they support analytics. These platforms are designed for deep insights, trend analysis, dashboards, and executive reporting. Unlike operational systems that focus on day-to-day transactions, analytical systems help organizations understand what has happened and why. Second, they rely on structured schemas. This means the data is modeled and organized in a way that makes it predictable, consistent, and optimized for querying. In environments like star or snowflake schemas, data is intentionally structured to support fast analytical workloads. And third, they store large amounts of historical data. This is key. Businesses need multi-year patterns, seasonality, customer behavior, long-term performance, and this historical depth is what enables forecasting, machine learning, and strategic decision-making. So when you think of analytical systems, think structured, reliable, and insight-driven, designed to help leaders make smarter, data-informed decisions. In this section, I want to introduce data lakes, a modern approach to storing and working with large volumes of information. A data lake is designed to store raw and unstructured data exactly as it is. Unlike a traditional database or data warehouse, we don't force the data into a predefined structure when it lands. This means logs, documents, images, IoT streams, JSON files, everything can be stored together without upfront modeling. Another key characteristic is that data lakes offer low-cost, high-capacity storage, often using cloud-based object storage like AWS S3, Azure Data Lake Storage, or Google Cloud Storage. This makes them ideal for organizations that need to retain massive amounts of data without spending heavily on traditional storage infrastructure. Data lakes also use a concept called schema on read, meaning the structure is applied only when the data is accessed or analyzed. This gives teams the flexibility to explore data in different ways, support data science initiatives, and adapt quickly as requirements evolve. Overall, data lakes are a powerful foundation for analytics, AI, machine learning, and long-term data retention, especially as organizations shift toward more data-driven decision-making. When we talk about moving data from one system to another, two of the most common approaches you'll hear about are ETL and ELT. These terms describe the order in which data is processed as it moves into a database, a data warehouse, or a data lake. ETL stands for extract, transform, load. In this model, I first extract data from the source systems, maybe an application, a database, or even logs. Then I transform that data before it ever reaches the destination. That transformation step might include cleaning the data, validating it, joining it with other sources, or applying rules and business logic. Finally, once the data is prepared, I load it into the target system. ETL is traditionally used with structured systems like data warehouses that expect clean, well-organized inputs. ELT stands for extract, load, transform. Here, the process is flipped. I extract the data just like before, but instead of transforming it first, I immediately load it, often into a high-power analytical environment like a cloud data warehouse or data lake. After it's loaded, I transform it using the processing power of the destination system. This approach is common in modern architectures because data lakes and cloud platforms can store raw data cheaply and process large volumes very efficiently. A simple way to think about the difference is this. ETL prepares data before it enters the house. ELT prepares the data after it's already inside. Both approaches are valid and widely used. The choice depends on your architecture, performance needs, governance requirements, and the types of analytics you want to support. Now let's talk about some of the core modeling approaches we use to design and understand data structures. First, ER diagrams, or entity relationship diagrams, are one of the most common ways we visualize how data entities relate to each other, things like customers, orders, or products. ER diagrams help us map out entities, attributes, and relationships before we ever build a database. They give us a clear picture of what data exists and how it connects. Next, normalized models are used primarily in transactional systems, systems designed for things like day-to-day operations, purchases, and updates. Normalization removes redundancy, structures data in multiple related tables, and protects data integrity. The goal is accuracy, consistency, and efficiency for high-volume reads and writes. Finally, dimensional models are used in analytical environments like data warehouses. Here, the goal is speed and usability for reporting and analytics. Dimensional models use concepts like fact tables and dimension tables to make querying fast and intuitive for business users. Instead of minimizing redundancy, dimensional models prioritize performance and simplicity. Together, these modeling methods help us structure data in the right way for the right purpose, whether it's powering real-time operations, enabling deep analytics, or simply giving us a visual map of how our data environment works. Now let's talk about four foundational concepts in data governance: definitions, lineage, ownership, and classification. These may seem simple, but they are absolutely essential to how an organization manages and protects its data. First, definitions. Every organization must clearly define what its data terms actually mean. If one team defines customer one way and another team defines it differently, the entire data ecosystem breaks down. So, having a shared vocabulary is critical for consistency, reporting, compliance, and analytics. Next is data lineage, which describes where data comes from, how it moves through systems, and how it changes along the way. When we can trace data from its origin all the way to its final destination, it becomes much easier to troubleshoot issues, validate accuracy, and prove compliance, especially in regulated environments. Then we have ownership. Every data set should have a clearly assigned owner. This isn't about being the boss of the data, it's about accountability. Owners ensure that data is accurate, updated, properly secured, and used appropriately. When ownership is unclear, data quality suffers and risk increases. And finally, classification. Classification labels data based on its sensitivity: public, internal, confidential, restricted, or whatever levels the organization adopts. This directly determines how the data must be handled, protected, and monitored. Without classification, we can't apply the right security controls, and we can't meet regulatory requirements. Together, these four elements form the backbone of trustworthy, well-governed data. They support stronger analytics, better decision-making, and improved security across the entire organization. When we talk about security and data architecture, we're really talking about protecting data throughout its entire lifecycle, from creation to storage to use to archival. Strong data security is a combination of technical controls, governance, and continuous monitoring. First, encryption is our baseline. We encrypt data at rest, in transit, and, when possible, in use. This ensures that even if data is intercepted or accessed improperly, it remains unreadable. Next, we apply RBAC, role-based access control. This means users only get the access they need, nothing more. Least privilege helps reduce insider threats and limits the blast radius of an account compromise. We also rely on tokenization, which replaces sensitive fields, like SSNs or credit card numbers, with non-sensitive tokens. This allows systems to function without exposing real data unnecessarily. Then we layer in monitoring. We continuously watch for suspicious access patterns, failed login attempts, unusual data movement, and unauthorized queries. Monitoring is essential for early detection of breaches. Finally, backups act as our safety net. If data is lost, corrupted, or impacted by ransomware, backups ensure we can restore quickly with minimal downtime. Together, these practices, encryption, RBAC, tokenization, monitoring, and backups, form the foundation of a secure data architecture. In this section, I want to introduce three major shifts happening in modern data architecture that every IT and cybersecurity leader needs to understand. First, serverless databases. These are fully managed database services where I don't have to think about servers, capacity planning, or infrastructure. The database automatically scales up or down based on demand, and I only pay for what I use. This is a huge advantage for modern applications because it removes operational overhead and lets teams focus on delivering value instead of managing hardware or performance tuning. Next, distributed data platforms. Instead of storing and processing data in one centralized location, distributed systems spread computation and storage across multiple nodes. This improves resilience, increases speed for large-scale workloads, and supports global availability. Platforms like Snowflake, Databricks, and BigQuery are built on these principles, and they enable massive parallel processing, which is critical for analytics, machine learning, and large enterprise data pipelines. Finally, AI-ready storage. As organizations adopt AI and machine learning, data storage needs to support unstructured data, high-throughput access, and large-scale parallel compute. AI-ready storage solutions make it easier to train models, run analytics, and integrate with tooling like vector databases, GPUs, and LLM pipelines. In short, they're designed from the ground up to support advanced data science workloads. Together, these trends, serverless, distributed, and AI-ready architectures, represent the future of enterprise data systems. They offer agility, scalability, and performance that traditional databases simply can't match. In this section, I want to briefly introduce four modern data architecture concepts that are increasingly shaping how organizations manage and scale their data environments. First, data mesh. Data mesh is a decentralized approach to data architecture. Instead of one central team owning all data, responsibility is pushed out to domain teams like finance, marketing, or operations who manage their data as a product. This model helps large organizations scale and reduces bottlenecks, but it also requires strong governance and clear standards. Next is data fabric. A data fabric is an integrated layer of technology that uses automation, metadata, and AI to connect data across environments. Cloud, on-prem, hybrid, you name it. Think of it as a connective tissue that enables seamless data access and governance across the enterprise. Then we have the lakehouse architecture. This combines the strengths of data warehouses and data lakes into one unified platform. A lakehouse supports both structured and unstructured data while also allowing high-performance analytics. It's become very popular because it eliminates duplicate storage and simplifies analytics pipelines. And finally, event-driven architectures. This model is all about responding to events in real time, things like sensor readings, user actions, or system activity. It's what enables modern systems to stream, analyze, and act on data instantly, which is essential for IoT, fraud detection, and dynamic cloud applications. Together, these architectural patterns give us the flexibility, scalability, and intelligence needed to support modern data-driven organizations. As we wrap up this module, here are the key concepts to remember. SQL versus NoSQL. SQL databases use structured, table-based schemas ideal for transactions and consistency. NoSQL databases offer flexible, schemaless structures built for scale, speed, and unstructured data. Data warehouses versus data lakes. Data warehouses store cleaned, structured data optimized for analytics and reporting. Data lakes store raw, unstructured, or semi-structured data, supporting large-scale ingestion and flexible analysis. ETL transforms data before loading it, suited for traditional warehouses. ELT loads data first and transforms later, ideal for cloud-scale analytics environments. Data models diagrams, normalized schemas, and dimensional models define how data is structured and related, supporting efficient operations and analytics. Metadata, definitions, lineage, ownership, and classification ensures consistency, governance, and trust in the data. Cloud data architecture patterns. Modern patterns like lakehouses, data fabric, data mesh, and event-driven designs bring scalability, agility, and integration with AI-ready platforms. Thank you for joining me for another episode of Technology and Cybersecurity Explained. I appreciate you taking the time to learn and grow with me. I look forward to seeing you in the next episode.